Today we're talking about half-lives. What we've learned so far is what an atom is, the structure of an atom, the subatomic particles of an atom, isotopes, and stability. Remember that some isotopes are more stable than others. Question is, how long does it take for an unstable isotope to decay into something more stable? And the answer is, it takes one half-life for half of that substance to decay. So what is a half-life? A half-life is the time it takes for half of a radioactive substance to decay. A half-life is fairly short for unstable elements, and it can be very long for the most stable isotopes of elements, even trillions of years, even longer than the time that the universe will exist. Let's take a look at some common half-lives. If we want to know the half-life of various isotopes, we can look them up in a table, such as this one produced by the NIST. You can see the left-hand column has the different isotopes. The center column has the half-life for those isotopes. So our first entry is H3, or tritium, and you can see its half-life is 4,500 plus or minus 8 days. So about 12 years. That's a pretty long half-life. Whereas right underneath it we have fluorine-18, which has a half-life of 1.8 hours. Depending on the half-life, these substances can have different uses. For example, chromium-51 has a half-life of 27.7 days. That makes it perfect for its use of tagging red blood cells to see where they move in a body and whether someone is bleeding internally. We can use this Georgia State website to take a look at the graph of decay. So we can see that after each of these time periods, which is a half-life, half of the substance has decayed. And thus we end up with this curve. This is what our half-life curves will always look like because of this pattern of decay. Notice that after one half-life, half of the original substance is remaining. After two half-lives, because now we're taking half of that half, 1/4 of the original substance is remaining. After 3 half-lives, an eighth. After 4 half-lives, a 16th. And after 5 half-lives, a 32nd. After 6 half-lives, it would be, right, 1/64th. Let's put into practice what we just used. This is a simulation published by Boston University, written by Andrew Duffy. What it gives us are 400 undecayed nuclei. And we can now make seconds go by. Notice that every second that goes by, a random set of the nuclei decay. How can we figure out the half-life? Well, if we started with 400 nuclei undecayed, when we reach 200 remaining, that is our half-life. Because half of the nuclei have decayed, the time that passed must be the half-life. Let's see what happens if we play out the rest of this. Notice that every time we pass one half-life, we have to half the number of samples remaining. If we half that number of samples remaining, we've passed the next half-life. If we half that number, we've passed the next half-life. Each time, half of the previous step remains. That's why we end up with this curve. This curve shows the change decreasing on a numerical level, even though percentage-wise it's the same. And one of the things you'll notice is as we get to the end, that last nuclei takes a long time to decay. In fact, it's only because of statistical variance that the last one decays at all. Because if you keep getting a half and a half and a half and a half, you technically will never run out of nuclei. To go through a couple half-life sample problems. Let's say that we have a certain radioactive material that has a half-life of 1 year. How much of this material will be left at the end of 4 years? So let's go ahead and say half-lives, years, and remaining amount. So after one half-life, that would be 1 year, because each half-life is 1 year, and we will end up with half of our initial amount. After 2 half-lives, this will be 2 years, we'll have 1/4 the original amount, because half of half is 1/4. After 3 half-lives, this would be 3 years, and we'd have 1/8 the amount. And after 4 half-lives, this would be 4 years in this case, half of 1/8 is 1/16. So our answer is 1/16 the original amount. Oops, wrote right over that. Let's go on to the next one. How long will it take 280 grams of a sample of iodine 131 to decay to 1/16 its original mass? So let's do half-life, year, and sample. Let's go ahead and start with 0 this time, just so we can write out our information. 0, 0, and this should be days, excuse me. And our sample is 280. We don't really need that because it just asks when do we get to 1/16. So after 1 half-life, that is 8.2 days, and we're going to have half of our sample. This would be the full amount. So half of this is 140. That would be half. After 2 half-lives, this will now be 16.4 days. And we'll have half of this sample, which is 70. And that's 1/4 of what we started with. After 3 half-lives, we'll have, that'll be another 8.2 days. And we'll have half of this sample. And now we're down to 1/8 of what we started with. And after 4 half-lives, let's add 8.2 onto that. Now we get half of this sample, which is 17.5, and that's 1/16. So, what's our question? How long will it take to decay to 1/16 its original mass? It will take 32.8 days. Finally, if osmium-182 has a half-life of 11.5 hours, how many grams of a 50-gram sample will have decayed after exactly 46 hours? All right. With 0 half-lives passed, that's been no time, and we started with 50 grams. After 1 half-life, that would be 11.5 hours, right? 11.5 hours. Now we're going to have half of the initial amount. After 2 half-lives, this will now be 23 hours. We'll have 12.5 remaining. After 3 half-lives, 23 plus 11 would be 34.5. And we'll have half of this amount, 6.25 grams. And after 4 half-lives, we'll add on another 11.5 hours. So that'd give us 46 hours. And we would have 3.125 grams remaining. Notice each time we cut the number in half. And each time we added, each half-life, we added 11.5 because that was our half-life. So how many grams would have decayed after 46 hours? Well, since we're left with 3.125 grams, 50 minus 3.125 would give us 46.8-ish. 46.875. That's how much decayed. So, to sum up, half-lives are a measurement of the time it takes for half of a radioactive isotope to decay. Half-lives are used not only in nuclear physics, but also in chemistry and in medicine, although that's metabolistic half-lives rather than decay half-lives. And you need to be able to do some basic half-life calculations, including figuring out the half-life based on a graph of decay, figuring out how much of a substance is left after a certain number of half-lives, figuring out how much of a substance is left after a certain amount of time given a set half-life, and figuring out how much of a substance you started with, if you know how much you ended with, how much time has passed, and the length of a half-life. If you have any questions, be sure to reach out.